Hello class, welcome, and I going to try out the webcast option here today, screencasting and picking up where we left off last week in terms of looking at sockets for internet programming. To start us off today, and we're going to actually cover a couple things today that have been kind of questions that we've left open, that some of which you've had in class, and and then things that you may have been otherwise wondering about, and fill in some gaps here, particularly talking about what we call name resolution, that is changing a name to an address. So to start out here, for example, I'm going to open up our client simple. If you remember, we were looking at this last week, and one of the things we had to do here was when we were looking at this, we had to take this address in and a port up here into our IPv4 adder struct object that basically then we were able to pass into connect, so that when we've created our socket, we could use a connect call to then for the case of TCP, we'd actually be establishing a connection. For the case of UDP, we would be directing where our datagrams would go, in other words, to which destination, IP address, and port. But this is a little bit kludgy in a couple ways. Number one, you can see that it's hard-coded. Okay, so number one, well, and that's not necessarily a problem for addresses per se. If you know you want to go to a particular address, that's okay. But in this case, one of the things we talked about earlier was the difference between IPv4 and IPv6, for example. Well, with the struct that we set up here, we get one or the other, and that's a little bit inflexible. Okay, and then also you may have some things built in, some fallbacks built in. So for example, if you try a given server, so this question came up last week in class, if you try a given address and for some reason the server has crashed on the other end or something like that, well, how do you account for that? How can you actually tell what's going on? So what we're going to do is we're going to take a look at these three lines right here, which were what we used to assign the address and the port to a structure that we then passed into connect. And we're going to change that around and use something a little bit more automatic and take into names. But first of all, let's actually take a step back and talk about what we call the domain name system. So first of all, let's think about how domain names work. You guys have all used them before. You use that when you go to any given website, for example, or when you're sending mail to a given email address. The tail end of it is in fact a domain name. Okay, we sometimes refer to that as simply domain in an email suffix. But the point is, those are all domain names as well. So if you take a domain name, and I've got a couple examples up here on the screen. I have www.foo.com, okay, at the very bottom left. And the way it works is each kind of word in the domain, we call those labels, and they're separated by dots in between when we represent them to humans. Similar to how we take the 4 bytes of IPv4 address and we put dots in between each of the bytes and create decimals. That's the human readable representation for an IP address. The human readable representation for a domain name is to take the individual labels and separate them by dots. Now conceptually what we're doing though is we actually have a name, and it actually is some part in a tree. Okay, so that's why, for example, you have a common suffix like edu. You have utah.edu for University of Utah, and then you have byu.edu for Brigham Young University, of course, and both of those have a common ancestor in that, and that is edu. So if we take a domain name from right to left, what we're doing is establishing from top to bottom the ancestry of this tree. Or if you go from left to right, you would be establishing the ancestry from bottom to top. Okay, in this case, let's take a look at that www.foo.com that I have mentioned. So you can see www.foo.com. If you strip the leftmost label, then you end up with foo.com. Okay, and then you strip foo from foo.com and you get com. And then actually if you take com away, there's something at the very end that's implicit, and we call that the root. Okay, the root is the top of the domain name system namespace hierarchy, and then from there we have top level domains, so com and net, edu, gov, etc. And it turns out that there used to be just a handful of these top level domains, some of the ones that I just mentioned. Several years ago, about 4 or 5 years ago now, it's been the group, the organization that administers the DNS root zone, okay, at the very top. And when I say zone, that's kind of a term that we use for kind of an administrated sorry, that's the word we use for a portion of the namespace that is administered by an organization. Okay, and the DNS root, just that part of it, is administered by a given organization, and there's actually it's represented by several different bodies there. But anyway, they came up with this idea of, hey, let's open this up for more than just these standard top-level domains. And so now we've gone from, I can't remember what exactly there were, maybe 20 to 30 of these domain names that are probably fairly common to you, .com, .net, .gov, .edu, etc. And then they opened it up to these applications to third parties, and now we have, I think, close to 1,500 or so. And so what we've seen is this kind of diversification of the DNS namespace. All right, but anyway, you should understand that notion that there is a root DNS domain or zone at the top of this namespace tree, and this is conceptually what it looks like for a given name when you trace it back. Trace it back to the top. You can see its entire ancestry just from knowing the name alone. Okay. Now what I've done is I mentioned that word zone just a minute ago. What happens is when you have at the very top, for example, at the root level, okay, so at the very top of the screen here, you can see at the DNS root there's also com and net in this example, and the organization that's responsible for the root zone, they're not also responsible for com and net. So what happens there is there's a administrative delegation, okay, that happens. So we call it delegation when you've said, okay, from this namespace downward, someone else is going to now take care of that. Now, as you can imagine, you would want to further delegate. So in the case of .com, which I have here before me, root has delegated the administrative responsibilities for .com to a given organization. Likewise, com has delegated administrative responsibilities for foo.com. So then when you have these three, the root, com, and foo.com, each of them are actually administered by different organizations. Okay. Now, when we get down to foo.com, we see this blue circle that I've kind of drawn in there in the slide, and below that you have two different names. Just because you have another label on the left-hand side, so www.foo.com and ns.foo.com, it doesn't necessarily mean there's another delegation of responsibility. In this particular case, foo.com would be the last point in the namespace where administrative responsibility has been delegated, so that means the names below that are in fact under administrative responsibility of foo.com. Now, of course, it could choose to delegate another part of the namespace, but in this example, it has not. Same thing with bar.com. You can see kind of a blue circle around that bar.com to indicate that is www.bar.com is under the same administrative responsibility as bar.com. And we would call these zones. And I could similarly draw one over just com or over just net. Or again, I could draw another one over baz.net and foo.baz.net, assuming that those are a single administrative responsibility for that given namespace. And again, we call that a DNS zone. Okay, so that's a little bit how the namespace hierarchy works in the DNS. And again, you can learn that just by looking at any given name. You can trace back its ancestry all the way to the root or the top of the DNS namespace hierarchy. All right, so let's take a minute. Understanding how that namespace works, let's now examine the different server roles and how we translate a given name to a given resource. Now we typically talk about the DNS as translating a name to an IP address, which coincides with the examples that we've done in class, but in truth it's actually an arbitrary resource. It's very common that it's an IP address, but it could be anything, and we'll show you some examples here as we go along. Okay, so we have three different roles, and I'll show you these in context here in the next slide. But first of all, we have what's called a stub resolver that has questions. It wants to know the answer to something. So this might be, the stub resolver might be something running on your laptop or on your computer, your desktop computer, and when you open your web browser, okay, your web browser is going to ask the stub resolver, hey, what's the answer? I'm going to www.byu.edu. What's the IP address corresponding to that? Okay, well, your browser then needs the stub resolver to be able to figure that out. Okay, so the stub resolver has the question given to it by the application. Okay, but then the stub resolver has to ask someone else. Okay, now eventually it has to go to what we call an authoritative server that has the answers. But in between the stub and the authoritative server, we have what's called a recursive server, and the recursive server sits between the stub and the authoritative server to help find the answers for the stub. So basically the recursive server is the workhorse to find those answers and knows how to do it. Stub resolver only knows how to ask a recursive server, and then the authoritative servers have the answer to begin with. They're just waiting to be asked. All right, and we've established this namespace hierarchy that I showed you in the previous slide. This is actually the way that the recursive servers know how to find their answers. They're going to begin their queries at the top of this hierarchy, and then they follow what we call these referrals downward. Okay, and what that means is that when namespace has been delegated, the server that they have asked, they don't know the answer per se, but they know where the recursive resolver can find it, and so they will send a quote-unquote referral to give them the names of the servers and the addresses of the servers where they can find it. Okay, so those are the different roles. Now let's look at this a little bit more systematically. Okay, so we have here our three roles that I just mentioned: a stub resolver, so that's like your computer; a recursive resolver, and may I add that the recursive resolver, if you bring your laptop on BYU campus, okay, this is the example of you will automatically be assigned by default to use BYU's recursive resolver. We sometimes refer to that as simply a DNS server, but in terms of roles of the DNS, it's more than that. It's the recursive resolver. At home, if you have Comcast, you'll likely be assigned Comcast's recursive resolver, or in other words, their DNS server. Okay. The authoritative servers, however, are not assigned to a given stub resolver. Those are just out there for anyone to ask them questions. Okay. All right. So that's how your recursive resolver is assigned. Okay. And now your stub resolver again wants to know the address or other resource pertaining to a given name. So in this particular case, we see that the stub resolver is asking the recursive resolver for www.foo.com. Let's say you'd pulled up foo.com in your browser. Now, the recursive resolver does cache, so it will hold on to responses that it gets, but let's assume here that it knows nothing at this point. It doesn't know anything about anything about domain names, including foo.com at this point. The only thing it does know at this point is it knows how to get to the DNS root servers. That's something that's predetermined in a recursive resolver. So let's assume that these are the names and addresses of our root servers. Okay, now these are not, in fact, the names and addresses, but we're going to make some. We're going to play with these numbers that we have here in front of us. Okay, the recursive resolver is going to ask one of these servers that it knows is authoritative for the root. In other words, has the information for the root zone or root domain. and it will get a response back. Now, because the root server has delegated the administrative responsibility for everything under .com to different servers, the root server cannot give, in fact, an answer to what the recursive resolver was asking. In other words, it doesn't know the answer to www.foo.com. It only knows that the com servers are being hosted, in this case, by two servers, and here are their names and addresses. Okay, a.tld.net and b.tld.net. Now, again, these are contrived names. The com servers actually have different names in this. This is just to illustrate a point here. Okay, so the recursive resolver gets back this referral, and it says, okay, now I'm going to ask one of these com servers. Okay, now that I know where com is, I can ask them the same question. Okay, and so knowing these com servers, the recursive resolver then asks its same question again. What's the address for www.foo.com? Okay, it selects one of these com servers and asks it that question. The com server then responds, hey, I don't know. All I know is that the foo.com authoritative servers are at this name and this address. Okay, and so now we see that foo.com has been given two names, okay, ns.foo.com and ns.bar.com with their corresponding addresses here. Again, this is completely contrived, but we're using it for example purposes. Okay, recursive server is going to do the same thing it did previously. Now that it has that referral for foo.com, it can ask one of those servers its same question again. So here's foo.com, and it asks one of those servers. Now, in this case, because it's asking for www.foo.com, but because there is no further administrative delegation, okay, in terms of like namespace has not further been delegated for www, the foo.com server can in fact answer. It knows the answer for www.foo.com, and the answer is, in this case, an IP address 10.0.0.1. After the recursive resolver gets this answer, it can then return it to the stub resolver, and then the stub resolver returns it back to the client. Okay, that is in essence happening more or less. And again, I mentioned there is some caching happening along the way, so it doesn't have to do this every time. It does remember certain things for a period of time. Okay, but that's in essence what's happening when you open an application and you need a domain name resolved to an address. Okay, now in terms of the DNS, okay, we are using a single request. Okay, and then you get a single response back. In other words, you just have to send a single message saying, what is this, the answer for this domain name that I'm looking up. Okay, and then the response is just a single response back. It's either a referral telling the recursive resolver where it can go to get this answer, okay, or it is the actual answer itself if it asked one of the authoritative servers for bar.com. Okay, now somebody asked in class last week, I probably got a few questions for that. What's the use of UDP if you have TCP? When we mentioned that UDP is unreliable, it's best effort transport, whereas TCP is reliable transport using this byte stream. Well, let's think about it in the context of what we know already about the DNS, and that is the fact that the DNS only requires that single request message, this single datagram to go out, and then you only need a single datagram response back. Well, if we think about the way TCP is set up, the fact is TCP requires us to do this three-way handshake before we can start. So basically, you have to do your SYN, your SYN-ACK, and your ACK, and that requires a single, what we call a round trip time. That means you actually have to go all the way out to the destination and get a response back. Now the ACK, you don't have to wait for that. You can just send your message right after the ACK. But the fact is you still have to wait for that round trip time. So instead of taking one round trip time to send a message and then get the message back, you have to do the complete round trip time for this three-way handshake first, and then do the round trip time for your actual request response. Okay, so when we talk about TCP, yes, it is reliable, and yes, UDP is not reliable. But if you can make an assumption that most of the time your datagrams will actually get there for UDP, and they do fit inside, the request and response do fit inside a single datagram, then isn't it just more efficient to first try UDP and only do TCP if you're having some type of trouble with that? That's actually similar to the way the DNS works. It's primarily UDP, and actually it does use TCP if it can't, it uses TCP actually if the message is too big for a UDP datagram. Okay, and that's, by the way, when I say too big, that's actually established something that's negotiated between the client and server. It's beyond the scope of what we're talking about here. But what you should know from this little summary here is that the DNS will primarily use UDP, but it can also use TCP as well for its communications. Okay, and it uses UDP because it's concise and it's quick. Okay. And okay, so now, but what is this message, this query that I mentioned, what does it actually consist of? So this DNS message, and that could be either a query or response, contains a header, which has some information associated with the message. So whether it's a query or response, for example, what the ID is. There's ID being a special identifier to identify that particular message, and then a few other options, which, by the way, you'll learn about in your upcoming lab when you're going to write a DNS resolver. There's much more specifics in the lab spec itself. Okay. Let's see. Then it also has, in addition to that header, it has several sections in the DNS message. Okay, one of them is the question section, and as you might guess, that is the name and the type, which we'll talk about in just a minute, that's being asked for. What are you actually trying to look up? So, in our example, we use www.foo.com, but could be, any domain name there that you're trying to look up. Okay, the answer section, if that section is populated, that's because the server that's returning the response is providing the answer for what you're looking up. Okay, but sometimes that section is empty because in the case of the referral that I mentioned, let's say you're asking the root, one of the root servers for www.foo.com. Of course, it doesn't know the answer, so it's not going to populate the answer section with anything that would be useful for this for this client. So it's going to leave it blank. But what it will populate instead is the authority section, and that's where it puts the information associated with the authoritative servers for foo.com or whatever the referral is for. Okay, and then the additional section contains other records. For example, if you're looking up mail server records, if you're wanting to send a message, an email message to somebody, that actually to learn which mail servers you should send to for a given domain, that requires a DNS lookup. Well, the DNS the DNS records associated with mail lookup are given by names, and so if you also want the addresses, so you don't have to do a second lookup, it could put those in the additional section, even though they're not directly part of the answer. It can say, and here's some other stuff you may want. So anyway, that's the biggest ones that you should know about are question, answer, and authority section, what those are. But let's talk about what those sections are a little bit more in detail here. Okay, and that's by discovering what a DNS record is. So each record in the DNS has an owner name. Okay, so that's when I say owner name, that's usually the name of the domain that you're doing the lookup on, or the name corresponding to the answer. Okay, there's also a time to live value. That's a value given in seconds, which is how long that a recursive server can actually hold on to that value before it's considered expired. Okay, so that's how caching works. You can the authoritative server, the administrator for that given domain can put this record on the authoritative server with a given time, so that it says, yeah, you can keep it for 15 minutes. We promise that that's good enough for what we're doing. Okay, so then after 15 minutes, it will have to go and try again, or something like that. Okay, record type is explained below in the next major bullet there. And actually, let's skip down there. So record types, these are where you look up, for example, an address versus something else. So one of the most common record types is type A, okay, which corresponds to an IPv4 address. Now, if you go back to that this fourth bullet down again, you can see that one of the parts of the record is a record data, which is the value being looked up. So you give it a name and a type, and then you get some answer back, and of course you have to have some value in there. So if you're looking up an IP address, the value would be the IP address of the name that you're looking up. But that value the type of the value and how long it is depends on the record type you're looking up. So for example, in the case of type A, an IPv4 address, the record data, or RData for short, is 4 bytes of IPv4 address, because as we mentioned in the last couple weeks, that an IPv4 address is 32 bits or 4 bytes. We also mentioned IPv6. There's a special record designated to look up an IPv6 address, and that is what we call a quad A record, which is shown using 4 A's together, and that's because there are 4 times as many bytes in an IPv6 address than there are in an IPv4 address. Okay, so a quad A record. As you might guess, the RData for this is now 16 bytes of address corresponding to IPv6 rather than IPv4. 2 other types that are useful. One of them you'll want to know for your lab is the type CNAME, which means that the owner name is actually an alias for something else. Okay, so in this case, the RData, rather than being 4 bytes of an actual address, it's saying, hey, this is another name, and you should really look up this other name instead, because this is just a placeholder name. A lot of times you'll see this with www, for example. Like, oh, the real name of this server is foobar.byu.edu, but we want to give it a nice clean name that everyone will recognize, and so what we do is we alias it using what's called a CNAME record. This is similar to like in your directory structure. If you've created a link, either a symbolic link in Unix or maybe an alias on your Mac or something like that, there's probably an equivalent in Windows, which I can't think of off the top of my head, shortcut I think. Then when you click on that, of course it doesn't, it takes you to the real location at that point, and that's similar to what a CNAME is doing. It's saying, hey, go look at this other thing, because that's really what you want. This name's just an alias for some other name. And then mail exchange records are a 4th type that I alluded to earlier, and those are something like if you're looking up something for the where to send mail for byu.edu, the DNS resolver would want to look up the MX records or mail exchange records for that. And those correspond to the name or names of server where mail can be sent for that given domain. So let's do a little bit of examples here. So let's see. So we have, let me pull up my VirtualBox here. So I'm going to send, we're going to do kind of trace down something for www.byu.edu. Now, the way it works in the command line, so dig is a command line tool. Its purpose is to send a single DNS query or message, okay, to a given server, and then it will receive the response and display it for you in human readable form. Okay, so if I want to send a message to one of the root servers, I'm going to do it by name here. I use this @ symbol here, and dig will send this message to a.rootservers.net, and then what I'm asking it for is www.byu.edu, and then I'm telling it type A. Okay, so now when I hit enter, what we're going to see is, here's some of the information up here at the top, the header information. You'll want to look at this a little bit more closely when we get into the lab, when you build the DNS resolver, but for right now it doesn't really matter. But remember, the root server that we've just queried does not know the answer. So what you don't see in here, you see the question section, okay, right here. What you don't see is an answer section that would immediately follow it if there were an answer section. But then you see this authority section. This authority section contains, if you look on the left-hand side, it says edu. Okay, so that's our owner name for these new records that I didn't explain earlier. They're called name server records. These are the records used to designate which servers are authoritative for the given name. And in this case, the given name is edu. So the root server is sending us back a response that says, I don't know the answer, indicated by no answer section. But I do know where the edu servers are, and they are at a.eduservers.net, c.eduservers.net, d.eduservers.net, etc. Okay, and it gives you 6 of them there. Now, what it does additionally to help you out is it says, oh, and by the way, here are the IP addresses so that you can reach those servers. Okay, there are some nuances with when you have names with learning the addresses, because eventually you need an address. Otherwise, you get this chicken and egg problem. Oh, I have an address, and or excuse me, I have a name. I'm looking up this name, and then the server gives you back another name, which you would have to go look up. There can be kind of a chicken and egg problem. Well, I'm not going to go into a lot of the specifics, except that the server can help you with that by also giving you the addresses at this point. Okay, so the root server gave us no answer because it didn't know it. It gave us in the authority section the referral to edu by telling us which servers are authoritative for edu. And then it also gave us in the additional section, kindly gave us some address. And you'll see, by the way, in there are some IPv4 addresses. And then at the very end, there's a quad A record, which corresponds to an IPv6 address. Okay, so edu servers have both types of addresses. They have both IPv4 and IPv6 connectivity. All right, that was our query to the root server for www.byu.edu. Let's go now and take one of those servers that we just got the referral to and ask that server. So we're going to ask a.eduservers.net that same question that we asked to the root server. So we're following the referral. We're doing what the recursive server would be doing now. Okay. Now, what we can see is, again, so here's our question section, which we would expect. It contains the question that we asked. Here is where our answer section would be if we actually got an answer, but we did not, because the edu servers do not know the answer for www.byu.edu. So here is the authority section instead, which does have a referral for us. Again, not an answer, but simply referral. Here's where the byu.edu servers are. They are at these 3 names, and then it kindly gave us the addresses associated with those names down here. Again, we can see 3 IPv4 servers and then 1 IPv6 server as well. Okay. All right, and so that's our query to the byu.edu server. Now we're going to try one last time and go to edns1.byu.edu. Okay, I'll move it up here so we can have the full screen, and we're going to ask our query one more time. And at this point, okay, let's look. We have our question here, okay, which we've seen before. That hasn't changed, but now we have something new. We have an answer section. Okay, and our answer section has a couple things in it. First of all, this is the name we were looking for, okay, over here on the left. But we see we don't have an A record corresponding to that. What we have is that C name record that I mentioned earlier. What that tells us is that this name on the left is actually an alias for another name, and it's specifically the name that it's an alias for is over here on the right. Now, I'm not going to go through this right now, but what our recursive server did right after it got the C name record, or what it's going to have to do is it's going to, if we were a recursive server, I should say, it would go right back to the other server and say, okay, now I'm looking for mg-web.byu.edu and for type A or IPv4 address, and it would give me the IP address in this case. Now you can see several organizations, they'll actually tie these together. So I'm going to do show you what intel.com looks like, for example, www.intel.com, because this is an interesting case where you have what we call a content delivery network, and what they're doing is they they actually have intel.com, so up here on this line right here, which is an alias for cn-www-ssl.intel.com.edgekey.net, some kind of longish name. Okay. Well, then a recursive resolver says, "Oh, well, I see. That's the name I need to be looking up now." So it looks up that one, but it learns that that one is also a a name here corresponding to some other. It's actually an alias for another long name here. So then it's going to look up that one, find out that one is also an alias to another name, and then finally we get to this last one, e11.b.akamaiedge.net, which corresponds to an IP address. So we actually went through 3 levels of indirection here to get the answer we were looking for. Okay, and sometimes that happens. You're actually going to have to handle this in your lab when you do this in the DNS server. But that is, in summary, what DNS resolution looks like. Okay, so let's go back and take this back now and see what this means in terms of our code. Okay, we learned a couple things in this. We learned a little bit about the DNS name resolution process. Okay, and we also learned about 2 different types of records in particular. Well, several, but the 2 in particular corresponding to addresses, the IPv4 address and the IPv6 address. Now, something to note here, this came up in the class last week also. Well, if a host has both IPv4 and IPv6 connectivity, how do we know which IP protocol we're going to use to connect to that host? Well, here's your key. It is the DNS, in fact. So what your resolver is doing is your resolver is going to ask a given question. Okay, so I'm going back to this byu.edu case, and it can say, by the way, I'm going to show you a new option here. And that is short. Rather than showing us all the sections, it's simply going to show us the answer, and it's just going to show us the data portion corresponding to that answer. So it's not going to show us all the other information. Okay. And by the way, if I'm not specifying a server to send the message to, it'll send it to my resolver, which will do all the work for me. So now I'm having dig, because I'm not specifying the server, it's acting as a stub resolver and having some other recursive resolver do the work for me. Okay, so now I say dig plus short to show me just the answer. www.byu.edu, type A. Okay, and it shows me again just those data. So it just those the data that I'm looking for, the R data. So it shows me the C name, okay, the canonical name corresponding to www.byu.edu because it's an alias, and then the address is corresponding to that. Okay, but now let's do if I do a quad A query. In this one, it turns up that there are no byu.edu addresses. Let's try another one here. And let's see. So sandia.gov is also an alias, and there's the IPv4 address corresponding to the alias. Let's see if we have an IPv6 address. Oh, there used to be one there. Now I'm a little ashamed. Let's do google.com. Okay. And make sure my network's working properly here. I thought Google had one. Let's see, www.biz.net. Something's stripping out IPv6 addresses from me, which I don't like, because I know that one has one. Let's do this. All right. I'm going to reach out to Google's resolver and see if I can get this. Okay, there we go. So now we're seeing here's a website which I happen to maintain called dnsviz.net. We can see if I do 2 different lookups from Google. From Google's, this is Google's DNS resolver. I'm asking them the question. They're looking it up for me, and we can see that I have both a quad A record, which corresponds to this IP address right here, and then I also have an A record that corresponds to this IP address right here. Okay, so now if your name, going back to the question, how do you know if something has IPv6 address or IPv4 only? The DNS is what helps us to learn that. Okay. Now, in the last couple minutes that we have remaining here, I know our time is short, but let's see if we can take a look at this client program one more time. And now we're going to come in here. What we had was, so remember our original client simple.c had hard-coded in there an IPv4 address struct, and we had to take an IPv4 address in from the command line and somehow convert it. Okay, we have this nifty function here called getaddrinfo. Okay, and specifically getaddrinfo is going to take in two string arguments at the beginning. Okay, the string arguments, the first one corresponds to a host name. You can actually put in an address there if you want, so we're not losing any functionality from what we had before, but you can also put in, if you want, a name. And now, but we don't have to specify which protocol even. Getaddrinfo will help us determine which protocols it has and return those back to us. Okay, so we have, and I'll show you what that means in just a moment here. Okay, so we have getaddrinfo right here, and then we have, first argument is our host name or IP address. Second argument is our port, which is also a string, which means we don't even have to do an A to I to convert it from what we're getting in on the command line. Okay, we can take a port number. We could also use an alias for a port. There are some aliases, although sometimes it's easier just to use the number itself. When I say aliases for a port, port 80 we said is the well-known HTTP port. You could actually write in HTTP here, and it should work to do what we would like if we wanted it to resolve to port 80. Okay, so it gives us additional flexibility in terms of what we're doing. We can just specify those two from the command line. Okay, the hints. What's this hint struct here? Okay, this is a the hints are a type that we call addrinfo struct. Okay, up here, and we're going to give it a few hints as to what we actually want it to do. Now, when we say address family unspecified, that means we're going to ask our stub resolver to look up either IPv4 or IPv6 addresses. It doesn't matter. It'll give us both of them, which means that we're actually we're not doing this explicitly, but our stub resolver is actually doing a lookup for type A and also for type quad A. So yes, that is two lookups to your recursive resolver for which it is looking things up. We're still telling it we want to use sockdgram. We haven't changed that. And then there might be some additional flags that we want. Usually you don't have to specify this protocol. Okay. Now, what does this do for us? Okay, so we've told it, here's the name, here's the port or the alias for the port, and then here's some hints which include that we don't care if it's IPv4 or IPv6, and and then we also have this thing called a result. Okay, the result up here, I'm scrolling up so you can see that's also a type. It's a reference to a type to a struct of type addrinfo, which has similar items in it. So let's look when we see we get result. Actually, result turns out to be a linked list, okay, of different addrinfo structs that have for us the things we would need now to create that socket and to connect on that socket. Remember, we had to hard code that stuff in there before and connect, and it was a little bit painful and it was inflexible. Now, getaddrinfo is doing all the work for us. We just had to give it some hints as to what we wanted. So it's filling in the family for us, okay, which is AF INET for IPv4 or AF INET 6 for IPv6. Okay, I'm going to pull up client. Oops, I'm going to pull up in a second window here client simple.c just so you can see what we ended up doing up here. So down here in this side socket, it's all populated from the members of this struct that was returned from the call to getaddrinfo right here, instead of us having to hard code and guess it. Okay, and then down here with connect, same thing. These are items in the struct itself that were populated by getaddrinfo. Now the reason why we're looping, if you can see, we're looping through, and what we're doing at each iteration is we're saying, get the next value. So it's looping like you would expect through a linked list. Okay. So that part is straightforward, but we're stopping and breaking out of the loop if we ever connect successfully. Okay, and so what that does, the third thing, it gives us flexibility, and is not just the whether it's IPv4 and IPv6, and the address family associated with that, but now also we get try them in order until something works. Okay, and now we getaddrinfo will give us an order that is most appropriate for us, and we can go through until it works. And we know, of course, it works if we get something that's greater than -1. Okay, so that is a summary of the DNS, okay, and how getaddrinfo can help us make our program a little bit more flexible in terms of detecting the capabilities for IPv4 and IPv6 and doing both of those queries for us. It can convert the names to addresses for us, and then provide all the information such that we can just pass it right in to connect when we're done. Now, the last thing, these are actually that linked list that we get is in fact created with malloc, so we've allocated memory for it on the heap. When we are done with it and we've already made our connections, there is this function called free_attrinfo, which will free up that memory that we've allocated, okay, so that it doesn't take up resources that we no longer need. So now, having added that code section, made that modification to our client, we're going to go back in now and test it out and see what we can do on the command line. So I've got our client.c with our new changes that we've made from client simple, wherein we've used the getaddrinfo function to populate for us and convert names to addresses rather than having to hard code them in, or and also be able to detect IPv4 and IPv6. By the way, I should note in this particular client that I'm using, I only have IPv4 connectivity, and so my system knows that, and my stub resolver will not actually look up IPv6 addresses, but that's another benefit to using getaddrinfo, is it will detect what connectivity you have, not only what connectivity the destination has. So in this particular case, this is what I will be anyway, so in this particular case, we will be using IPv4, but if I were to bring this to another location that had IPv6, then we could try it from there. So, and it would connect over IPv6. But now let's give this a go. So I'm doing roam.dco.net, which is my remote server, and here on this side I have it set up. If you remember, we have it set up right now for socdgram, which is UDP. So I've got the -u flag in there, and then I'm listening, and we're listening on port 5599. And again, here I'm specifying, rather than an IP address, I'm specifying name, and which we couldn't do with client before, with client simple, because we were hard coding an IP address. Oops, let's try this again. Uh-oh, what am I missing here? Okay, so we are taking in name and port. We're using socdgram. We're looping through. We're connecting, which means just telling it where we're going to send our datagrams in UDP. Oh, it's because I said port 1. I need our other, our real port there. Okay. And there we get our 1, 2, 3, 4, now that I've specified an actual port and not port 1, which is what I was trying to do previously. And so the datagrams were likely getting there, but nothing was listening on port 1, and so that's why I was doing that. So, all right, so, and that's, yeah, we have some issues with UDP and having to start over, but anyway, that's how things look when we are there. When we use getaddrinfo, so we can use names now, and we could even, by the way, let me, oh, I don't have an alias for that port or for that service, or I would demonstrate that for you, but we'll leave it at that. Show you how we can use names and do automatic address detection for our destination. Okay. All right, we'll leave it at that. Thanks, and I hope this was useful for you.